So so where this came from, this presentation is on the Raspberry Pi forum. Richard was talking about his LED neopixel issue, and I said, well, there is another way we could do it. Not saying that what he's doing doesn't work. He's just giving an alternate. So this presentation is sort of associated with the alternate, but more importantly, I'm trying to do is show how to actually read the data tables of chips to understand how to design an alternative. In fact, you'll see here I've actually got 2 or 3 different ways of doing it, but it's how to actually read the data sheet to actually work out. So the issue for me was what's the design brief? So it was basically to multiplex one control data line out of a Pi into 3 separate neopixel strings, one at a time. So it's just a demultiplexer. The two we're using that analog switch that 4051 which is using 2 of the strings. Input data line of the strings it just floats. So if it's on a board where these lines are reasonably close, there'll be capacitance between them, and it's the rise time of the data line that determines not the frequency of the data line, but the rise time of the signal that determines how well that coupling is going to work. And since it's driven from a Pi, which is a modern device, it's got a very fast rise time. So the capacitance would look like low impedance to a signal. And that's one reason I've suggested to him to put a 1K resistor to earth, was it would be a really low impedance and would completely knock out any signal coming through the straight capacitance. And the third thing in the design brief was address this issue about the Pi is working at 3.3 volts and the neopixels are running at 5. And while they do work, if you connect them together, it's not guaranteed. So it's well, let's throw that in the design brief at the same time. So what I find with in the designs, things will work, and that's fine if you've got you just got one at home. But if you make 1,000 of these things and we're going to production, you're going to see a distribution of some at the top end of their performance level, some at the bottom end, and equally things in critical applications, they might work, but they also might misbehave once a month or once a fortnight or something like that. You tend not to see that at home, whereas in a critical application, you will. And, again, that would be seen as non-conformance. So while it's not mandatory to do this last one, it was just, well, let's see how we can deal with that at the same time. So I said, they will work. There's some traps, and that's what I'm talking about here. Now, the thing is, on the NeoPixel, a 1 is defined as 0.7 times the voltage you're applying to it, which is 3.5 volts. And the Pi is only putting out just under 3.3. It's not a full 3.3, but it's just under. So there's this gap between 3.3 and 3.5 where you could get misbehavior, where and it's only because the neopixels you've actually got are better than their specification. But if they were at minimum spec, they wouldn't work. So looking at this issue about multiplexing, and Richard was using binary coded decimal to 3 lines to get 8, to select one of 8, or 2 lines to select 4. I was thinking about this and saying, well, actually, with only 3 neopixel strings, if you go BCD, you need 2 lines, 2 control lines. If you just drive them direct and say, got 3 lines, I've got 3 neopixel strings, I'll use 3 GPIO outputs. But there's no real gain or no real loss in efficiency there. But if you're up at, say, 5 or 6 or 8 or more, then clearly BCD output's clearly the way to go. So I wasn't too hung up about getting binary coded output of the Pi to select from the chip selection. So this is a table comparing. I'm actually having trouble because I've got some of the Zoom stuff over. So what I've got here is a table of different family chips. So on the left, the first column here is this traditional 5-volt TTL logic. The next one is the TTL with the low power Schottky variety. The third column is a 74HC, which is effectively a CMOS technology. And it's still in the same pin layout and pin compatible with the original TTL, the 74 series TTL. And on the right-hand side is the 4000 series. And so Richard's in that 4051, it's in that family. And so you can see here the voltage, the top line, the top row, is saying this is the potential voltages these chips can work at as a demultiplexer. And so the problem we had with the original TTL is it was 5 volts, with sometimes plus or minus 0.25 or sometimes 0.5 volts. It was pretty tightly controlled. On the right-hand side, the CMOS was the 4000 series, was really forgiving. You could go anywhere up to sort of 18 volts. But this interesting one is this HC series allows you up to 6 volts. So the real question is which one of these would you select from? Because effectively there is the same technologies, the same chip combinations in all these families. So what we're looking at here is, let's look at this issue of this 3.3 to 5 volt translation and how do we deal with that? So if you look on the bottom here where it says logic outputs at 5 volts, so I'm applying 5 volts to this chip. It says here that the 74 series, the original transistor logic, for a 1 output, it could be as low as 2.4 volts. It may not get anywhere near 5 volts. And a 0 could be as high as 0.4. So clearly that's not going to interface to the neopixels. The low power Schottky gets up at 3.5. It can go as low as 0.25. But this is the interesting one, is this the CMOS version, H74HC series, it will go as high as 7. It will only go, remember this is the minimum level of the output voltage for a 1. It'll only come down as low as 4.4 volts. And that's quite interesting because that means it's above the required voltage for the neopixel, which I'm actually quoting down the bottom. You can see here, down the bottom, I'm saying that the neopixel needs 0.7 times its rail voltage, so 3.5 volts minimum. You've got to be above 3.5 volts to guarantee a 1. And that's the problem with a Pi. It's only can get to 3.3. You run the risk that it won't work. So this third column here, the 74HC series, where it gets to 4.4 and will always be below 0.1, is an interesting family to pick from. So looking at those characteristics here in this left-hand column, where did they come from? How did I find them? So if I go to a data sheet out of that book I've got, and I come over here, the first thing is the absolute maximum ratings of this chip is 7 volts, but you don't want to run it at those, you don't want to apply 7 volts to it. So you come to the next section, which is the recommended operating condition. There it is, there's supply voltage, nominal 5 volts, 4.5 to 5.5. That's these sort of numbers. So that's where you get the nominal voltage. And here underneath it this is the recommended high level voltage for a 1, and the recommended low level voltage for a 0. So that, you can see here in my previous thing, VIH and VIL, voltage input high, voltage input low. And that's these two here. And then on the next page, the thing is the V output high and V output low. Come across here, I said it's going to be a minimum of 2.4 volts for VOH, and worst case is 0.4 for 0. It could be below 0.4 volts. So these are the pages in a data sheet that I go looking for to work out this interfacing. And by the way, when I just had a quick look up that chip that Richard's using, the 4051, the analog passband frequency is up to 40 megahertz. It's actually quite wide. It's actually a wide band on the analog circuit. So whatever you put in from a digital stream coming in will actually pass. It will pass that through pretty well, actually. I'm quite surprised.
So can I just ask, you called it a demultiplexer earlier. I thought I always understood it, the SN74, I understood it as a level shifter, but I've ordered quite a few and I've used them on quite a few of my neopixels. And I see on the CPC site, it's called an octal bus transceiver with 3-state output. So I guess it's it all means the same thing, I assume.
Well, tri-state or 3-state output means that and these are not in that family. So tri-state output says if you turn off the output enable pin, the output floats of the chip. And what that's used for is where you've got multiple chips driving one data bus. Say in a computer, you've got multiple disk drives back onto the main motherboard. You enable one hard drive to talk to the bus, and all the chips in the other devices are all disabled. So only one chip is driving the ribbon cable. These are not tri-state devices. These are permanently connected. The outputs of these are permanently connected. And of course, something with a tri-state output will have a different set of performance. Here these electrical characteristics.
But sorry, on your previous page you had the SN74 series. So this is an SN74. Is that?
I'm just talking about the 7400, the 74XX series.
Oh, okay. All right. I was referring to the I think one or two slides before this. Okay.
Like this.
Yes, that was this one there. So at the top there, the 74HC. So I use 74HCT245N for my neopixels.
Right. Okay.
But as I say, I understood it just to be a level shifter. But you were calling it a D.
Yeah, but there's a 74HC00 or 01, 02, all the way up. A third of this book's in the HC series. So the difference between them is the logic between the inputs and the outputs. The family's got the same output characteristic, electrical characteristics are the same.
Okay.
So the question is, which one in the family would we pick? So the LED strings that Richard's got, and you can see that on his on his oscilloscope, it puts out a signal. It starts at 0, goes up to a 1, and then down. And the width of the signal determines whether it's a 1 or a 0. So it's a return to 0, and it wants to sit at 0 volts when it's idle. In fact, what it's doing is a reset. You can see that on Richard's oscilloscope. You see on the left-hand side, there's 2 wider pulses. They are 1s, and the rest of them are all 0s. So that's how this thing is working. So an important part of this design's got to be that when it's disabled, the output's got to be 0. It can't be a 1. So one option is to use an AND gate. On the left-hand side, I'm just doing the typical AND logic, 0, 0, 0 out. It's only when you get 1, 1, you get a 1 out. So I'm proposing that you could use that here by using one input as the enable disable for the string, and using the data from the pi 0 and 1 to output. And it's pretty simple. So you would end up with a circuit like that. Here's the data coming from the pi at the very top, fed to all the 3 AND gates, and you just select which one you want to enable. Pretty simple stuff. And I've shown at the bottom to don't forget any parts of the package that are not used, connect them to 0 volts, etc. Otherwise, it'll sit there as an oscillator and cause all sorts of grief, particularly if the chip is an inverting type device. Equally, you could use a NOR gate. And so the purpose of this is you've got a design like the previous one, and you go to something like RS or, or Element 14 looking for chips, and they're not available. So here's an alternative. You could use a NOR gate, and in that one, the logic's reversed. So because it's got negative logic, I'm actually doing an inversion to start with. Coming back, you can see that when the output here is a 1, the output doesn't change, it's locked on 0. And if I enable it by turning the input to 0, the pi goes to 0, the outputs are inverted. So that's the reason I've got this inverter on the front end. So that'll work quite fine. And then the third way of doing it, and literally only found this looking in this book. I find the books are actually much better to find alternatives. So here's a BCD Decimal Decoder. It's actually was, I think, used primarily on 7-segment displays or selecting, enabling in multiplexing for displays. So you can see what's happening as in these 4 columns on the left-hand side, the address is working through, 0, 1, 2, 3. One of these outputs is going low, one at a time, down this diagonal line. You can see the sort of complexity of the chip. But again, it's a simple 14-pin chip. So again, how could we use that? So putting the data line on, the data from the Pi on A3, taking A2 to 0, just holding that at 0, and then just using the 2 other lines to address it. And again, you'd get one of 4 selected, one of 4 neopixel strings selected, and then also as the data is going here from low to high in the A3 column, the output's going from low to high. So it's in phase, and that would work. And clearly what you're saying about another chip, equally that would work. So there's multiple ways of doing it. And in this day and age with chip shortages, it's a matter of finding something you can get hold of. Not you need some alternative designs. So that was as simple as that. I had to stop sharing.
So Tony, do you still end up with the floating? You still end up with the floating problem, do you? Floating voltage.
No. Okay, let me go back here. So on all of these, if you look at any of these, you'll see that when the device is disabled, this top column here, so when the Pi is telling this chip, this AND gate to be disabled, the output from this chip is a 0.
Oh, okay,
it's not floating. And that's being fed permanently to, there's 1-for-1 relationship between a chip, a logic gate and a data in to a neopixel string. So they don't, none of them ever float. Okay. And that's the common, that's a common theme through. So if you like, this sort of design stops them floating. There's a low impedance drive. You've got the family that, like the HC series, 74HC series, gives you the voltage compatibility. It's the combination of those two that allows us to meet the design brief.
Very cool. I'll try this as well.
So you become RS's best customer, hey?
It's a very special day when you get it delivered from RS.
Yeah.
Amazon is normal, but getting something from RS is good.
I gave them, I can tell you now, I gave Amazon hammering while I was in the UK. Bought power saws, all sorts of things.
Cool. Is there any questions for Tony or myself or comments? Everyone's had enough of neopixels.
Yeah.
The only thing that occurred to me was that you have the chips where you put in a binary address in parallel in order to select your output line. And with those, as you change the address, you are liable to get brief glitches. And Tony's design doesn't have that, because you can raise the enable for the signal to go to the first string. Then you can lower that before you raise separately the signal for the next. So, you know, it just seems like a great design.
One of the ways you can overcome that on any of these designs is there's a reset time on the neopixel. So if you do an address change, you know, change selecting from string 1 to string 2, and it did do a glitch, before you start outputting data to it, you would just hold it low for, say, 1/10 of a second. And that would give a chance for all the neopixels to reset, and then they'll accept data and not see the glitch as part of the data structure. So I think Richard's done something like that. He's put a time delay. I remember seeing on Facebook he was talking about putting a time delay in somewhere.
Yeah, that's right. Just after. So I do the data send, and then immediately after that, I can do the switch. Sorry, wait 1/10 of a second and then do the switch.
Yeah.
Don't know if 1/10 of a second is the minimum, but that seemed to work.
Yeah. The other thing is the question is, why couldn't you get the Pi to output 3 neopixel strings? My understanding is the way it's working. There's a pulse width modulating circuit inside the Pi, 2 hardware, not software, but 2 hardware PWM circuits, and they can be selected to pin 18, and I can't remember, I think it's pin 20 or something like that. And I use them in some of my machines where I use them as a. What they've done here is they can take that PWM driver and chain it up to do direct memory access, so the Pi doesn't have to write to the output in real time at 800 kilohertz or it's doing 1 megahertz. It blocks up the data in memory, and then enables the PWM circuit to do a direct memory access and just output that, how many thousand bits it's got to do. And there's only 2 of them. So I think in a presentation I did about a year or 2 ago, I showed how to modify the driver, and you could actually set up a second one. But there's a limit. It would be 2 only.
Yeah. Yeah, it'd be interesting to try that as well. Many things to try. Any other questions, comments? Yeah. Yeah, thanks a lot, Tony. That was I like your design.
Okay,
Just save me a lot of time.
I'm going to head off. I've got to go to work.
Okay, thanks.
It's 7:30 tomorrow, so it's going to be a nice
day. Thanks, Tony. Have a good day.
Okay, cheers, guys.